Hello everyone, I'm Shohei Mori from Graz University of Technology, Austria. I'm going to present our work, Multi-Layer Scene Representation from Composed Focal Stacks. This is a collaborative work with Keio University in Japan and Flinders University in Australia. Multi-layer scene representation is a 3D image consisting of multiple of RGB alpha layers slicing over the scene. Depending on the shape of the proxy, it is called multi-plane images MPI or multi-sphere images MSI. Rendering can be very fast due to its simplicity. We warp individual images and composite them by alpha blending. Convolutional neural network is often used to analyze 3D scene points at a depth, meaning that each image of multi-view inputs is warped to pre-calculated depth to let the CNN see if the colors from different observations agree at the same points. To enable this, an intermediate data structure called plane sweep volume is created. This is a duplicated input images, but it's shifted depending on the layer depth. While it allows the network to check the disparities, the input data easily occupies the GPU memory. Let's say with more than 5 input views, the system becomes infeasible. Our idea is to simply summing up all the plane sweep volumes that results in a focal stack and investigate its advantages in the context of virtual and augmented reality. A focal stack is a series of images differently focused at individual layer depths. Now, the data is lightweight, but we found more than that. In this research, we propose a view synthesis pipeline. Namely, we propose a system that composes a focal stack from multi-view images to subsequently infer a multi-plane image MPI. We discuss theoretical bounds to form focal stacks that are sufficient and appropriate for generating MPIs using a single UNet-like network. We demonstrate the advantages of our approach for MPI generation from focal stacks. In particular, we discuss its robustness against pose and image noises, its benefits to the memory footprint, and the data capturing process. Finally, we demonstrate and discuss the benefits of our approach for photorealistic VR applications. Forming a focal stack from multi-view images is known as a synthetic aperture photography technique that mimics a real lens camera. Dots on the camera plane on the left represent cameras facing towards the scene, and dots on the focal plane on the right represents pixels to be rendered. Similarly to a real lens camera, we can define an aperture which filters out cameras outside of it. Let's now focus these 2 pixels for brevity. Since the focal plane is located at far, 1 pixel catches mostly on the same surface point of an object. But on the other hand, the other pixel collects multiple different surface colors. Therefore, the object near the focal plane gets sharper, and everything away from the plane gets blurry. If we move the focal plane to the frontal object gets sharper, and the back object gets blurry. Potentially synthetic aperture collects multiple scene observations from an image to form an image. That is, once focal stack is formed, locally existing noises can be diminished. This is advantageous for us because we can train our network using a synthetic multi-view dataset without any noises. However, we need to be careful on how to form a focal stack to avoid forcing unnecessarily complex tasks to our network. Here's a view frustum with a given aperture and focus distance Zi. Given a set of multi-view images, we can create an image with defocus using synthetic aperture at the depth. Since we can define an aperture, our image captures sharp scene points within the depth of field in blue. If we set a larger aperture, the depth of field gets shallower, as in a real lens camera. If we set a focal stack sparsely over the depth, then some scene points never get sharp in the focal stack. To avoid letting our network to learn how to deblur such scene points, we would rather want dense depth of fields without any gaps in between. Please refer to our paper to know how to calculate and form such a focal stack. To cover a large area and to take view-dependent effects into account, we employ the baseline length between cameras from the local light field fusion paper by Mildenhall. Now we know how to create our focal stacks, we need to train our network. The task for our network is to create a multiplane image from a focal stack. We used a U-net-like network structure as our first attempt, or we believed that U-net is powerful enough for our task. We take color space perceptual loss and L1 loss for color reconstruction, and histogram loss to keep consistent color balancing. We took the overall loss against the original multi-view images and the focal stack. Our dataset consists of multi-view images rendered using Blender and Thingy 10K models placed randomly in a scene. One of example images is shown here. We evaluated multiple aspects of our view synthesis pipeline. For example, we investigated if the number of input views supports the planoptic sampling theory in our dataset. We discuss if the robustness against local noises artificially inserted into our dataset is guaranteed and to which extent. We demonstrated the entire view synthesis pipeline that includes real scene data capturing using a tracked smartphone, focal stack generation, and MPI inferencing and rendering. Overall, we confirmed that our approach can achieve more robust multiplane image inferencing and rendering against local noises in comparison to existing work like local light field fusion and IBRNet. But for the sake of time, here we report only our user-involved study. We discussed if our dataset and data capturing scheme makes multi-view image capture easier. Here we prepared a baseline capture system from local light field fusion. The baseline approach places 3D camera axes to show that where the user needs to place their smartphones in the air. In our approach, users can randomly move around within a flat cube and that represents a camera plane. Since the 3D camera annotations and their intervals are scene scale dependent, we prepared desktop-sized and room-sized scenes. We performed two-way repeated measures ANOVA within 2 factors of method and scene scale. We assumed that first we would observe less task load in hours due to the less restrictive 3D alignment task, and second, scene scale has an impact in task load due to the scale changes in visualization. The statistical analysis results supported both hypotheses, but no interaction. In conclusion, we proposed our view synthesis pipeline using a focal stack composed from a set of multi-view images. We clarified how the focal stack needs to be formed and investigated the advantages in many aspects. Applications may include denoising MPI from dark scene photos, MPI from an optical focal stack, and wide field of view rendering as shown on the right. We also found many rooms to investigate further. For example, a focal stack is just an approximation of the original images. Therefore, more sophisticated network design would be needed. More efficient data recording would further enhance our approach. Thank you for your attention. We are happy to discuss our work.